In the previous lectures, we classified partial differential equations and we primarily classified second order quasi-linear partial differential equations. So these equations were classified as elliptic, parabolic, and hyperbolic. So all our transport phenomena fall in either of these three categories. But the fact that we don't have simple solutions, or we are for the fact we are not able to find analytical solution for all complicated equations. For instance, we don't have complete analytical solutions for Navier-Stokes equations. So we resort to approximate solutions to these partial differential equations. Now, approximate solutions can be as close to as exact solutions. So what should be the objective of finding our approximate solution? Our prime most objective should be to minimize the error. That is, the approximate solution should be as close to the exact solution as possible, although it will never be equal to the exact solution because we are not able to find the exact solution. So in this direction, we have a very powerful mathematical tool, and that is called calculus of variations. That will help us in formulating the minimization principle. Minimization principle in general, and particularly we shall be interested in error minimization. So we want to minimize the error. And also this is closely related to the principle of least action. So this is the principle of least action. This principle unifies all dynamic laws, whether it is classical mechanics or quantum mechanical systems. So what we can have is principle of least action states that there is minimization of some action whenever there's a dynamics going on. Likewise, when a system is in static equilibrium, we know that in static equilibrium we have something that is at a minimum, and that we call as, say, potential energy. Likewise, whenever system is in motion, there is something that is minimized or extrematized in general. And generally it is minimization, that's why it is called principle of least action. Now to get some physical insight into this principle in general and to the error minimization principle, what we shall do is we shall take an example. Say t1 is a time instant, any arbitrary time instant, and say t2 is any arbitrary time instant t2. So what I am doing here is I am tracking the trajectory or path of a particle moving in phase space. So what is happening here is at t1 the particle is here, at t2 the particle is here. It could follow any of the paths which joins these 2 points t1 and t2. These could be, there could be n infinite many possible paths which could be followed, but it takes this specific path when it evolves from time t1 to t2. Now why does this do so? For instance, in physics what we say is, say if we have a ball here, say I have a ball here, I simply allow it to freely fall. What do I know? It will simply follow this path. Now if I have some initial velocity to this wall, what will happen? It will follow a trajectory which essentially looks like a parabola. So there is a characteristic path followed in each case, and we have the question that why it is always a characteristic path which is followed, not some other path. So the answer to this is, in all dynamical systems there's something that is minimized and there's some governing law which dictates what trajectory it will follow. Now what I am doing here is I am drawing a generalized, I'm taking a generalized coordinates, say q and q dot. So these are generalized coordinates and these are generalized velocities, and these are independent variables. Now this is an important aspect which you need to take into consideration. When I say coordinates and velocities are independent, at first instant it might seem to be weird because all of us know from mathematics that q dot is essentially the first derivative with respect to time of q. So how can q and q dot be independent? Now this shall become much more clear if you see these two examples. In this case, the velocity or the trajectory that the ball follows depends on its initial coordinates. Say we have the same initial coordinates and we throw the ball once freely and the other with some velocity v. In both the cases, I get a different trajectory. So I have at my disposal to choose what velocity I choose. So velocity and the location, they are independent coordinates, and this should be always kept in mind. Now I define a quantity called L, and this is called the Lagrangian, such that it is a function of q, q dot, and t. Now what happens is this quantity is minimized as I go from t1 to t2. So L dt, this is some action that is function of t1 and t2, and principle of least action says this action should be minimized. Now what I am doing here is I am redrawing the trajectory. So this is instant t1, this is instant t2, and say this is the trajectory that the system or the particle actually takes. And these are all possible trajectories that could have been taken. Now it takes this trajectory. So by a principle of virtual work, what I know that displacements at these 2 points, that is at instant t1 and t2, because I know the location at t1 and t2, I don't know this trajectory. So if I say variation of q means the coordinates. Variation of q should be equal to 0 at t1. Likewise, variation of q should be equal to 0 at time t2. Because I have already specified that at time t1 and t2, these are the deterministic locations or q's for the particle. But at all other instants between these t1 and t2, I don't know where will be the particle, whether it is following this path, this path, this path, any of these paths. So what do I know? I want to minimize what? I will take the first order variation of this q dot t dt, and this should be equal to 0. Now this is the first order variation, and this is, although it is variation is applying to this integral, but because I have freedom to choose t1 and t2, if this is t1, I could have chosen this as t2 instead of this, then also this should hold true. So it says that this entire path could be broken down into n number of smaller paths, and this should be true for each such smaller path as well. So this holds true for each and every point. So what does that tell you? This will give you a differential equation, that is at each instant how the particle will evolve will be there through some physical law. Now if I take the first order variation, what do I get? L is a function of q dot t, and this first order variation has similar mathematical properties as of a derivative. So what I'm doing here is, say I write down like this delta. So I'm writing down here delta L. So delta L should be equal to, now L is a function of Q. So I'm writing down here delta Q plus L is also function of Q dot, delta Q dot, and I will not take, so I could have taken this as well, delta L by delta T, but I will not take this term because actually I cannot have any variation in T, because this is what I am controlling. I am changing T and finding out what is change in L with respect to Q and Q dot. So please remember, this T is the arena in which this change is happening. So this cannot be taken. So I am left with these two terms. And moreover, one thing more should be clear in your mind, that delta L by delta Q dot into delta Q dot is something which I need to further solve. I can apply the chain rule, or I can apply the integration by parts. So I will do it in subsequent steps. So now I am writing down this entire thing again. Now what I have is delta L is equal to delta L Q dot T from T1 to T2 dt is equal to 0. So I know that I am taking delta inside. So I have curly L by curly Q delta Q plus curly L by curly Q dot delta Q dot. Then I have this dt T1 to T2 is equal to 0. Now this is already in the simplest format, but I could actually reduce Q dot to Q. So I will integrate this by parts, treating what? This as the first function and this as the second function. Now what do my first and second function? What was the motivation behind choosing this as second function? Because I want to reduce one order of derivative here. And as a side note, those who are not familiar with the basic integration by parts, now what we have is, say, f and g are two functions. I take a derivative of this product. What do I have? F dg by dx plus g df by dx. If I take an antiderivative, what do I get? D by dx fg dx integral is equal to f dg by dx integral plus g df by dx integral. So what do I get here? I get fg is equal to f dg by dx plus g df by dx. So what do I need to find out? For instance, I'm manipulating this. So what do I get? F dg by dx into dx is equal to fg minus g df by dx into dx. So I have actually derived the formula for integration by parts by simply invoking this principle. Now I'm applying this identity to my this principle of least action, which we have already stated. Now you can see that I'm applying this identity to this part. This part remains as such because this is already in the simplest format. So I am rewriting this as same. And now in this is the first function and this is the second function. So this is first, this is the second function. So what do I know from my identity? That first function is this f, this is second function. So I have first function, integral of second function. So first function is delta L by delta Q dot. Then what is this? First function. Then integral of second function. So what is second function here? Delta Q dot. And what do I have here? Minus. Now this is integral of second function. So what does that tell me? Integral of second function means here is the second function. So integral of second function into what is this? Differential of first function. So first function here is this. So differential of first function dt. So now what about this term? Now this term essentially, what does this equal to? So I know that delta L by delta Q dot. Now the integral of this will be delta Q from T1 to T2. What do I know? Delta Q at T1 and delta Q at T2 both are equal to 0. So this boundary term will essentially become 0. So what I'm left with this term and this term, and this entire thing is equal to 0. So I'm now here it should have been the integral of this, and this should have been here delta Q only. So delta Q dt in brackets parenthesis curly L by curly Q dot. So what I can do here is I can take out variation of Q outside. Now this is true for any arbitrary variation in Q. So if this is to be 0 always, it means it is only possible if the integrand itself is 0. So what we are left with is curly L by curly Q is equal to d by dt curly L by curly Q dot. And this is called the Euler-Lagrange equation.